What if everything we thought we knew about the most extreme objects in the universe was wrong? What if the cosmic monsters we've been calling black holes for nearly a century are something far stranger, far more terrifying, and fundamentally different from what generations of physicists have imagined? Picture this: right now, at this very moment, there might be objects lurking in the depths of space that make black holes look tame by comparison. Objects that don't just swallow light and matter into oblivion, but do something far more unsettling. Something that challenges the very fabric of reality itself. For decades, we've been told that black holes are the ultimate cosmic predators, the final gravitational prisons from which nothing can escape. We've imagined them as bottomless pits in spacetime, regions where the laws of physics break down into mathematical gibberish, where infinity becomes real and time itself ceases to have meaning. But what if this entire picture is fundamentally flawed? What if nature abhors these infinities as much as our equations do? What if, instead of black holes, the universe has created something even more exotic, something that solves the paradoxes that have plagued theoretical physics for generations while simultaneously opening up new abysses of mystery? Welcome to the world of Gravastars, the gravitational vacuum stars that might be the universe's answer to the impossible contradictions buried at the heart of black hole theory. These are not your grandfather's cosmic objects. These are entities that exist on the knife's edge between existence and non-existence, between matter and vacuum, between our universe and something else entirely. They are bubbles of nothing wrapped in shells of everything, structures so dense and so strange that they make black holes seem almost ordinary by comparison. The story begins, as so many revolutionary ideas in physics do, with a problem that wouldn't go away. For nearly 100 years, ever since Karl Schwarzschild first derived his famous solution to Einstein's field equations while serving in the German army during World War I, physicists have grappled with the singularity problem. What happens at the center of a black hole? The mathematics says that matter collapses to a point of infinite density, infinite curvature, infinite temperature. Infinity. That word that makes every physicist's skin crawl, because when infinity appears in your equations, it's usually nature's way of telling you that something has gone terribly wrong with your theory. Think about it this way: imagine you're trying to describe what happens when you divide a pizza among your friends. The math works perfectly fine for 2 friends, 3 friends, even 100 friends. But what happens when you try to divide that pizza among 0 friends? You get infinity. Nonsense. A breakdown in the logic of the system. This is exactly what happens at the center of a black hole according to classical general relativity. The equations that work so beautifully everywhere else in the universe simply give up and spit out infinity, and physicists have been deeply uncomfortable with this for generations. But here's where the story gets really interesting. What if nature itself is just as uncomfortable with infinities as physicists are? What if the universe has found a way to avoid these mathematical catastrophes altogether? Enter the Gravastar, a theoretical object first proposed by physicists Paul Mazur and Emil Motola in the early years of the 21st century. These researchers asked a simple but profound question: what if, instead of collapsing all the way down to a singularity, matter does something completely different at the final moment? What if, just when you think everything is about to be crushed into infinite density, nature plays a cosmic trick? Imagine you're watching a star die. Not just any star, but a massive one, perhaps 20 or 30 times the mass of our Sun. This stellar giant has spent millions of years fighting against its own gravity, burning nuclear fuel in its core to generate the outward pressure that keeps it from collapsing. But eventually, inevitably, the fuel runs out. The nuclear fires that held gravity at bay flicker and die. And then comes the collapse. In conventional black hole theory, this is straightforward: the core implodes, rebounds, blows off the outer layers in a spectacular supernova, and what's left continues collapsing past the point of no return, forming an event horizon and eventually crunching down to a singularity at the center. But Gravastars tell a different story. A strange story. A story that seems almost impossible until you realize it might be the only story that makes sense. As the collapsing matter approaches what would normally become the event horizon, something extraordinary happens. The intense gravitational pressure doesn't just compress the matter further. Instead, it triggers a phase transition, a fundamental change in the nature of reality itself at that location. The vacuum energy, that mysterious quantum field that permeates all of space, suddenly flips. It goes from positive pressure to negative pressure, from trying to expand space to trying to contract it, from pushing outward to pulling inward with a force that rivals gravity itself. This isn't just speculation. This is quantum field theory taken seriously in the most extreme environments imaginable. You see, the vacuum isn't empty. That's one of the most profound discoveries of 20th century physics. Even in the darkest, coldest, most isolated region of space, the quantum vacuum is seething with activity. Virtual particles pop into existence and annihilate in time scales so brief they make a nanosecond seem like an eternity. These quantum fluctuations give the vacuum energy, and in certain circumstances, this energy can become dominant, overwhelming even the crushing force of gravity. So picture this: as matter collapses toward what would have been a black hole, the vacuum energy suddenly switches sign. It becomes negative, creating a region of repulsive gravity. Not attractive gravity like we're used to, but repulsive, pushing matter away with tremendous force. The collapsing material finds itself caught between two competing forces, gravity pulling it inward and this exotic vacuum energy pushing it outward. And in that cosmic tug-of-war, something remarkable emerges. The matter doesn't collapse all the way to a point. Instead, it forms a thin shell, a surface of incredibly dense material surrounding a core of negative energy vacuum. This is the Gravastar. A bubble of false vacuum, of negative energy spacetime, wrapped in a membrane of matter compressed to almost unimaginable densities. The interior isn't a singularity. It's a region where spacetime itself has entered a different phase, like water turning to ice, except this is far more fundamental. This is the fabric of reality itself transforming into something alien, something that pushes outward instead of pulling inward, something that might be connected to the dark energy that astronomers tell us is accelerating the expansion of our entire universe. But here's where gravastars become truly terrifying, truly stranger than the black holes they replace. The surface of a gravastar, that thin shell of ultra-dense matter, isn't just any surface. It's a place where the laws of physics are stretched to their breaking point. The density is so extreme that atoms can't exist. Nuclei can't exist. Even the quarks that make up protons and neutrons are crushed together into configurations never before seen in nature. The matter in this shell exists in a state that makes neutron stars look fluffy by comparison, makes white dwarfs seem as insubstantial as gossamer. And yet, despite this extreme density, or perhaps because of it, the surface is stable. The negative pressure from the vacuum interior perfectly balances the inward pull of gravity and the outward pressure of the compressed matter. It's a three-way balance, a cosmic standoff, and the result is an object that can exist indefinitely without collapsing further. No singularity. No infinite density. No mathematical breakdown. Just an incredibly strange, incredibly dense, incredibly stable structure that looks almost exactly like a black hole from the outside. That last part is crucial. That's what makes gravastars so insidious. So difficult to detect, so challenging to distinguish from the black holes we think we've been observing all these years. From a distance, a gravastar and a black hole look essentially identical. Both have the same mass. Both warp spacetime in the same way. Both bend light around them in the same characteristic patterns. Both have surfaces that light cannot escape from. The gravitational field outside a gravastar is indistinguishable from the gravitational field outside a black hole of the same mass. This means that every supposed black hole observation we've made, every X-ray binary, every supermassive object at the center of galaxies, every gravitational wave detection from merging compact objects could actually be gravastars instead? We wouldn't know the difference. Not from the outside. Not with current technology. The cosmic joke might be on us. We might have been looking at gravastars all along and calling them black holes because we didn't know any better. Think about what this means. Really think about it. For decades, astronomers have been mapping what they call black holes throughout our galaxy and beyond. They've found stellar mass black holes in binary systems, tearing material away from companion stars. They've found intermediate mass black holes lurking in globular clusters. They've found supermassive black holes at the centers of galaxies, including the one at the heart of our own Milky Way, that monster we call Sagittarius A star. They've even managed to image what they believe is the shadow of a black hole at the center of the galaxy M87, that famous orange ring that captured the world's imagination a few years ago. But what if all of these objects, every single one, is actually a gravastar? What if the universe simply doesn't allow singularities to form, and every time we think we're seeing a black hole, we're actually seeing this other thing, this structure with no singularity, no interior, just a shell and a bubble of quantum vacuum? It would be one of the greatest misunderstandings in the history of science, up there with thinking the Earth was the center of the universe or believing that time was absolute and universal. Now let's venture deeper into territories that conventional black hole physics cannot navigate. Consider the quantum mechanics of what happens inside a gravastar's core. This isn't merely empty space with negative energy. This is a domain where the vacuum itself has undergone a fundamental transformation, where the Higgs field might take on different values, where the masses of particles could theoretically differ from what we measure in our laboratories. Inside that bubble, the laws of particle physics might be subtly or even dramatically altered. What would this mean? Imagine a region, however small and however well hidden behind an impenetrable shell, where electrons have different masses. Where quarks bind together with different force constants. Where the fundamental constants of nature, those numbers we inscribe in textbooks as immutable, become variables. This possibility terrifies and exhilarates physicists in equal measure. It suggests that our universe is not a single, uniform playing field but rather contains pockets, isolated domains, where reality operates by different rules. Some theoretical physicists have speculated that these interior regions might connect to other parts of spacetime through mechanisms we don't yet understand. Not wormholes in the classical sense, those speculative tunnels through spacetime that science fiction loves, but something more subtle. Perhaps the negative energy vacuum inside a gravastar is continuously linked to the dark energy permeating our cosmos, acting as a kind of reservoir or exchange mechanism. Perhaps energy flows between these isolated bubbles and the broader universe through quantum channels we haven't detected. This raises an extraordinary question: could gravastars be influencing the expansion of the universe itself? We know that dark energy constitutes roughly 70% of all energy in the cosmos, driving galaxies apart at an accelerating rate. We know that this dark energy behaves like a negative pressure, exactly the property that characterizes the interior of a gravastar. If there are billions upon billions of gravastars scattered throughout the universe, each containing a bubble of negative energy vacuum, could their collective effect contribute to or even explain dark energy? The mathematics here become dizzyingly complex. You're trying to account for the local concentration of vacuum energy inside compact objects while simultaneously explaining how this relates to the smooth, uniform distribution of dark energy we observe on cosmological scales. The scales differ by factors of billions. Gravastars are kilometers across while the observable universe spans tens of billions of light-years. Connecting these scales requires sophisticated mathematical machinery and physical insights that are still being developed. Yet the possibility tantalizes. What if dark energy isn't some mysterious field permeating all of space uniformly, but rather the cumulative effect of countless localized vacuum phase transitions that occurred during the formation of compact objects throughout cosmic history? What if every Gravistar is a tiny seed of the same phenomenon that's ripping the universe apart on the largest scales? This would be a profound unification, connecting the physics of ultradense matter to the cosmology of universal expansion. But let's turn our attention to another unsettling aspect of Gravastars, their potential instabilities. While the basic Gravistar model suggests stability, deeper analyses reveal that this stability might be more fragile than initially thought. The shell surrounding the vacuum core must maintain an extraordinarily precise balance. Any fluctuation in the vacuum energy, any quantum tunneling event that shifts the interior to a different energy state, any external perturbation that compresses or heats the shell, could potentially destabilize the entire structure. What happens when a Gravistar becomes unstable? The scenarios range from the merely dramatic to the cosmically catastrophic. In one possibility, the shell might undergo a phase transition of its own, converting from normal dense matter into something even more exotic, quark matter, strange matter, or configurations we haven't even named yet. This transition could release enormous amounts of energy, potentially observable as peculiar types of explosions or emission that don't fit into our current catalog of astrophysical phenomena. In another scenario, more terrifying still, the vacuum bubble itself might tunnel to a lower energy state. Vacuum phase transitions can be explosive. We think such a transition might have occurred in the first fraction of a second after the Big Bang, ending the inflationary epoch. If a similar transition occurred inside a Gravistar, the energy release would be concentrated in a tiny volume, potentially creating a shockwave that tears through the shell and erupts into the surrounding space. The energy scales involved could rival or exceed those of supernovae, creating transient events that might already be hiding in our astronomical data, misidentified as something more conventional. There's an even more disturbing possibility that some researchers have contemplated, though it remains highly speculative. What if the vacuum inside a Gravistar isn't stable at all, but metastable? What if it represents a false vacuum, a local minimum in the energy landscape but not the global minimum? In that case, quantum mechanics tells us that the vacuum could spontaneously tunnel to the true ground state, even without external triggers. This is called vacuum decay, and in the context of cosmology, it's a scenario that could literally end the universe as we know it. Now, before we descend into apocalyptic panic, let's be clear, if Gravastars with metastable interiors were common and prone to catastrophic vacuum decay, we probably would have noticed by now. The fact that the universe still exists and operates according to stable laws suggests that either Gravastars don't exist, or their vacuum cores are genuinely stable, or any instabilities operate on timescales far longer than the current age of the universe. But the possibility lurks there in the mathematics, a reminder that we're dealing with phenomena at the absolute edge of physical theory. Consider also the question of rotation. Real astrophysical objects spin. They acquire angular momentum during formation and retain it unless they can transfer it elsewhere. A rotating black hole is described by the Kerr solution to Einstein's equations, and it has fascinatingly complex properties, multiple horizons, regions where spacetime is dragged around by the spinning mass, even a zone called the ergosphere where it's impossible to remain stationary relative to distant observers. What about rotating Gravastars? The mathematics become ferociously difficult. You have a spinning shell of matter with its own internal structure and dynamics, surrounding a rotating vacuum bubble with repulsive gravity. The balance that maintains the structure in the non-rotating case becomes more delicate when angular momentum enters the picture. The shell might develop instabilities at high rotation rates, perhaps shedding matter or radiation to slow itself down. Or it might support entirely new configurations that have no black hole analogues. Some theoretical work suggests that rapidly rotating Gravastars might be unable to exist at all beyond a certain spin threshold. The centrifugal forces might overwhelm the delicate balance maintaining the structure, causing the shell to fragment or the vacuum core to become unstable. If this is true, it provides a potential observational test. If we find compact objects spinning at rates that Gravastars cannot support, those objects must be something else. Conversely, If we observe a suspicious lack of rapidly spinning compact objects, it might hint that gravastars are real and subject to these spin limits. Then there's the question of electric charge. In principle, matter can carry electric charge, and if you compressed charged matter into a gravastar shell, the object would have a net electric charge. However, astrophysical objects tend to be electrically neutral because opposite charges attract and neutralize each other. Any significant charge would attract oppositely charged particles from the surrounding space, quickly neutralizing the object. So charged gravastars probably don't exist in nature, or exist only briefly before being neutralized. Yet the theoretical possibility remains interesting. A charged gravastar would have different properties than a charged black hole. The electromagnetic field would interact with the shell's matter in complex ways. The vacuum core might respond to electromagnetic stress differently than to pure gravitational stress. These differences, though unlikely to manifest in real astronomical objects, tell us about the range of possible configurations that physical law permits. Let's shift our focus to the most dramatic events involving gravastars, collisions and mergers. When two black holes spiral together and merge, they produce gravitational waves that we can now detect with instruments like LIGO and Virgo. These detections have revolutionized astronomy, opening an entirely new window onto the universe. But what if some of these events actually involve gravastars instead of black holes? The inspiral phase would be nearly identical. Two massive, compact objects orbiting each other lose energy to gravitational waves and spiral inward, exactly as general relativity predicts regardless of whether they're black holes or gravastars. But the final moments of merger and the subsequent ring-down might differ in subtle but potentially detectable ways. When two gravastars collide, their shells physically interact. Matter from one shell encounters matter from the other at velocities approaching the speed of light. The energies involved are almost unimaginable. Particles are accelerated to energies that dwarf anything achievable in human-built accelerators. The colliding matter might produce bursts of high-energy radiation, gamma rays, X-rays, perhaps even more exotic particles. Simultaneously, the vacuum bubbles inside the two gravastars would begin to interact, their negative energy regions merging or interfering in ways that depend sensitively on the quantum field theory governing the phase transition. The merged object would need to settle into a new equilibrium. The combined shell would oscillate, ringing like a bell struck by an enormous hammer. These oscillations would produce gravitational waves with characteristic frequencies determined by the shell's properties, its mass, its thickness, its equation of state. By analyzing the gravitational wave signal carefully, particularly the ring-down phase, we might be able to distinguish gravastar mergers from black hole mergers. This is easier said than done. The differences might be small, buried in the noise of the detectors, or masked by our incomplete understanding of how matter behaves at nuclear densities and beyond. But as our gravitational wave detectors improve in sensitivity and as we collect more merger events to analyze, patterns might emerge. We might find that certain features in the ring-down signals are more common than black hole theory predicts, or that the spectrum of oscillation frequencies doesn't quite match expectations. These subtle discrepancies could be our first solid evidence for gravastars. There's another potential signature in mergers, the production of electromagnetic counterparts. When two black holes merge in isolation, they produce only gravitational waves, no light. But if the merging objects are gravastars with matter shells, the collision might produce significant electromagnetic emission. This could explain why some gravitational wave events seem to have faint electromagnetic counterparts that don't fit standard models. Perhaps we're seeing the shells of colliding gravastars producing brief flashes of radiation as their ultradense matter interacts. Now let's contemplate an even more exotic scenario, the accretion of matter onto gravastars. When gas from a companion star or from the interstellar medium falls toward a compact object, it doesn't fall straight in. Angular momentum causes it to spiral, forming an accretion disk, a whirlpool of matter gradually working its way inward while heating up through friction and releasing enormous amounts of energy as X-rays and other radiation. For black holes, this process is well studied. The matter spirals inward until it reaches the innermost stable circular orbit, then plunges across the event horizon and disappears from view. The innermost stable orbit depends on the black hole's mass and spin, and by studying the X-ray emission from the inner accretion disk, astronomers can infer properties of the black hole. But for gravastars, the endpoint is different. There's no event horizon to cross. Instead, the accreting matter eventually crashes into the shell. What happens then? Does the matter merge smoothly with the shell, adding to its mass and changing its structure? Does it splash, creating shock waves and turbulence on the surface? Does it heat the shell to such extreme temperatures that exotic particle production occurs, perhaps creating matter-antimatter pairs or more unusual quantum states? The answers depend on details we don't yet know: the precise equation of state of the shell matter, the efficiency of energy dissipation, the role of magnetic fields and other non-gravitational forces. But the key point is that accretion onto a gravastar should produce observable signatures that differ from accretion onto a black hole, at least in subtle ways. The X-ray spectrum might differ. The variability patterns might show different timescales or correlations. There might be emission lines produced by matter just before it hits the shell that would be absent for black holes. Detecting these differences requires sophisticated observations and detailed modeling. It requires teasing apart the complex physics of accretion flows, magnetic fields, radiation transport, and relativistic effects to isolate the signature of the central object. This is difficult work, but it's the kind of detective work that astronomers excel at. Given enough data and enough computational resources to model different scenarios, we can constrain the properties of these objects and perhaps determine whether they're black holes or something else. There's a philosophical dimension to the gravastar hypothesis that deserves our attention. For centuries, science has been stripping away anthropocentric illusions, revealing that humans occupy no special place in the cosmos. We're not at the center of the universe. Our sun is an ordinary star in an ordinary galaxy. The matter we're made of is the same matter that comprises stars and planets. Even the elements in our bodies were forged in stellar furnaces and supernova explosions. But singularities represented a different kind of challenge to this view. They seemed to suggest that the universe contained true infinities, places where physical law broke down completely, where mathematics itself gave nonsensical answers. This bothered many physicists because it implied a fundamental incompleteness in our description of nature. If our best theories predict singularities, and singularities are unphysical, then our best theories must be incomplete. Gravastars offer a way out of this philosophical dilemma. They suggest that nature, in her infinite cleverness, has found a mechanism to avoid singularities altogether. The universe doesn't contain mathematical infinities, just extremely large but finite quantities. Physical law remains valid everywhere, even in the most extreme environments. The mathematical breakdown at singularities is revealed as an artifact of approximation, of pushing classical general relativity beyond its domain of validity. If gravastars are real, they vindicate a certain aesthetic sense about how the universe should work. Many physicists feel, perhaps unjustifiably but nonetheless deeply, that nature should be elegant, that the laws of physics should be complete and consistent everywhere. Singularities offend this aesthetic. They feel like mistakes, like places where the cosmic operating system has crashed. Gravastars, by eliminating singularities, restore our faith that the universe is fundamentally comprehensible, that there are no places where understanding simply ends. But this philosophical satisfaction comes with a price: increased complexity. The gravastar picture requires vacuum phase transitions, exotic equations of state, quantum field theory in curved spacetime. It trades the conceptual simplicity of classical black holes for a richer, more complex description involving multiple branches of physics working in concert. Is this trade worthwhile? Does nature prioritize avoiding infinities over maintaining conceptual simplicity? We don't know. Nature doesn't consult our aesthetic preferences. She simply is what she is, and our job is to figure out her properties through observation and experiment. Let's turn now to the implications for fundamental physics if gravastars prove real. The existence of stable vacuum phase transitions in strong gravitational fields would tell us profound things about the quantum vacuum. It would confirm that the vacuum can exist in multiple states with different energy densities and different properties. It would prove that these states can coexist in the same universe, separated by domain walls or transition regions. And it would demonstrate that gravitational stress can induce transitions between these states. This has implications far beyond gravastars. It relates to our understanding of the early universe, where vacuum phase transitions might have played crucial roles in determining the properties of space and matter. It connects to particle physics, where the Higgs mechanism involves vacuum fields taking on particular values that give particles their masses. It ties into cosmology and the mystery of dark energy. The vacuum isn't just empty space, it's a dynamical entity with structure and properties, and gravastars might be our best laboratory for studying its behavior under extreme conditions. Furthermore, if gravastars exist and contain regions where physical constants differ from their normal values, this opens up extraordinary possibilities. Could life, for instance, exist in some unimaginably different form in these exotic regions? Almost certainly not. The conditions are far too extreme, the volumes too small, the isolation too complete. But the mere fact that the laws of physics might be different in these tiny pockets of universe forces us to reconsider what we mean by the laws of physics. Are they truly universal, or are they contingent, depending on the state of vacuum and field configurations in a given region? These are deep waters, touching on questions about the nature of physical law itself, about why our universe has the particular constants and symmetries it does, about whether other configurations are possible. String theory and its relatives have long suggested that there might be a vast landscape of possible vacuum states, each with different low-energy physics. Gravastars, if real, might provide the first concrete evidence that this landscape is physically meaningful, not just a mathematical curiosity. Consider also what gravastars might teach us about quantum information. The black hole information paradox has vexed physicists for decades. When matter falls into a black hole, the information about its quantum state seems to disappear, violating the principle that information is conserved. Various resolutions have been proposed: information encoded in Hawking radiation, holography on the event horizon, firewalls at the boundary, but none entirely satisfactory. Gravastars sidestep this paradox elegantly. With no true event horizon, information never disappears from the observable universe. It might be scrambled, encoded in incredibly complex ways on the gravastar surface or in the quantum state of the shell, but it's not destroyed. The universe's information ledger remains balanced. This is not just a technical point, it's a profound statement about the consistency of quantum mechanics with gravitational physics. If gravastars preserve information while mimicking black holes in most observable respects, they represent a resolution to one of the deepest puzzles in theoretical physics. They show that general relativity and quantum mechanics can coexist without contradiction, at least in this context. This doesn't mean we have a complete theory of quantum gravity, we don't, but it suggests that the apparent contradictions might be less severe than feared, that there are regimes where semi-classical approximations work well enough to capture the essential physics. Now, as we approach the conclusion of our journey through the strange landscape of gravastars, let's consider what they mean for the future of physics and astronomy. If the next generation of observations reveals clear evidence for gravastars, it will transform multiple fields simultaneously. Astrophysics will need new models for stellar evolution endpoints and galactic dynamics. Gravitational wave astronomy will need refined templates for merger signals. Cosmology might need to reconsider the connections between local vacuum energy and global dark energy. But beyond the technical implications, there's something deeper. The discovery of gravastars would represent a triumph of theoretical physics, of taking mathematical structures seriously even when they predict phenomena far removed from everyday experience. It would show that the language of mathematics really does describe reality at its most fundamental levels, that our equations are not just convenient fictions but genuine insights into the nature of existence. At the same time, it would humble us. For decades, we thought we understood what lies at the centers of galaxies and in the remnants of dead stars. We called these objects black holes with confidence, built elaborate theories around them, wrote them into textbooks. To discover we were wrong, or at least incomplete, would remind us that science is always provisional, always open to revision, always subject to correction by new observations. This is not a weakness of science, it's its greatest strength. Unlike systems of thought based on authority or revelation, science builds in mechanisms for self-correction. When nature contradicts our theories, we change the theories, not nature. We follow the evidence wherever it leads, even if it leads to conclusions we didn't expect or didn't want. Gravastars, whether they exist or not, have already served a valuable purpose. They've forced us to think carefully about extreme physics, to question assumptions we'd taken for granted, to explore the full range of possibilities allowed by our theories. They've connected different branches of physics in unexpected ways, from quantum field theory to general relativity to cosmology. They've generated predictions that can be tested observationally, turning abstract mathematics into concrete science. And perhaps most importantly, they've reminded us that the universe is under no obligation to match our expectations. Nature is what she is, indifferent to our preferences and assumptions. Our job is to observe carefully, think clearly, calculate precisely, and above all, remain open to surprise. The history of science is filled with discoveries that nobody anticipated, from the expanding universe to quantum entanglement to dark energy. Gravastars might be the next entry in that list, or they might not. Only nature knows, and she reveals her secrets slowly, grudgingly, only to those patient and clever enough to ask the right questions. As we stand here at this moment in history, with instruments capable of probing the cosmos with unprecedented precision, with theories sophisticated enough to make testable predictions about extreme phenomena, with computational power to simulate the most complex physical processes, we have an extraordinary opportunity. We can potentially answer questions that previous generations could only wonder about. We can test the behavior of space-time and matter under conditions that dwarf anything achievable in laboratories. We can map the landscape of possible objects that physics permits to exist. Gravastars are part of this grand investigation, this human project of understanding the cosmos. They represent a possibility, a question mark, a challenge to conventional thinking. They embody the spirit of scientific inquiry, taking ideas seriously, following them to their logical conclusions, then checking whether reality agrees. This process has worked remarkably well for centuries, expanding our knowledge from the scale of falling apples to the scale of the observable universe, from the behavior of everyday objects to the quantum realm where particles tunnel through barriers and exist in superpositions of states. What will we find when we look more carefully at the compact objects scattered throughout space? Will they be black holes, those elegant solutions to Einstein's equations with their event horizons and singularities? Will they be gravastars, those exotic structures balancing on the edge between different phases of reality? Will they be something else entirely, some phenomenon we haven't yet imagined? The answer awaits us in the data, in gravitational wave signals yet to be analyzed, in X-ray spectra yet to be measured, in observations yet to be made. And when we finally know, when the evidence accumulates to the point where the conclusion becomes inescapable, we will have learned something profound about the universe. We will understand what happens when matter becomes maximally compressed, when gravity becomes maximally strong, when the quantum and gravitational realms meet in the most dramatic possible way. We will have pushed our knowledge to one of the ultimate frontiers of physics. But even then, even when we think we understand these extreme objects, the universe will still hold mysteries. There will be deeper questions about the nature of spacetime at the smallest scales, about the origin of physical laws, about why the universe exists at all rather than nothing. There will be puzzles about consciousness and observation, about the role of information in physics, about the relationship between mathematics and reality. Science is not a destination but a journey, and each answer opens new questions, each solved mystery reveals deeper mysteries beneath. This is the glory and the challenge of the scientific endeavor. We're not seeking to close the book on knowledge but to keep turning pages, to keep exploring, to keep discovering. Gravastars are one page in this endless book, one question among countless questions, one mystery among the vast array of mysteries that the universe presents to curious minds. And so we continue forward, armed with curiosity and mathematics, with telescopes and theories, with patience and ingenuity. We observe the heavens. We run calculations. We build models. We test predictions. We argue and debate and collaborate and compete, all in service of understanding what is real and true about the cosmos we inhabit. This is our nature as thinking beings, to seek understanding, to build knowledge, to push against the boundaries of ignorance. Gravastars, terrifying in their strangeness, beautiful in their mathematical structure, remain for now a possibility hovering at the edge of knowledge. They might be real. They might be phantoms. They might be partially real in ways we haven't yet conceived. But the question of their existence is answerable, the mystery is penetrable, the truth is discoverable. And that, ultimately, is what matters. In a universe of matter and energy, of spacetime and quantum fields, of stars and galaxies spread across billions of light-years, we find ourselves here, now, asking questions about the most extreme phenomena imaginable. We wonder about objects so dense that reality itself changes phase at their cores. We contemplate structures that challenge our understanding of space and time. We seek to know whether nature allows singularities or finds clever ways to avoid them. These are not idle questions. They're investigations into the deep grammar of existence, into the rules and possibilities that govern what can be. And whether gravastars exist or not, whether they prove to be the answer to old questions or merely beautiful mathematical curiosities, the act of investigating them, of taking these ideas seriously and checking them against reality, is itself worthwhile. It's an expression of what we are at our best, curious, rational, creative, persistent. It's a demonstration that even the most extreme, most alien, most terrifying aspects of the universe can be approached with thought and observation, can be understood at least partially, can be incorporated into our ever-expanding picture of how nature works. So let us continue asking. Let us continue observing. Let us continue calculating. Let us continue wondering about gravastars and black holes, about dark energy and quantum fields, about the origin of the cosmos and its ultimate fate. Let us embrace both the terror and the wonder of a universe far stranger than our ancestors imagined, far more complex than our theories fully capture, far more magnificent than our words can adequately express. For in this pursuit of understanding, in this reaching beyond ourselves to grasp truths about the external world, we find perhaps our deepest purpose, to be consciousness contemplating cosmos, to be the universe beginning to understand itself.